In this lecture, we are going to discuss about differential amplifier. Actually, it is the second module. Okay, second half of the second module. First half is current mirror circuit, and the same thing, the differential amplifier, what we are learning in this module itself, we will apply it in the third module, that is operational amplifier. Both are same, only slight difference will be there. So both the module are carrying same idea. Op-amp is nothing but a differential amplifier itself. Some modification will be there in that circuit. For two-stage op-amp is there we will use two differential amplifier, or the cascaded system we will use. Okay, so in this session we will discuss about differential amplifier, so the concept of differential signaling, then MOS differential amplifier, or it's an example of a differential amplifier, or how we will implement a differential amplifier, basic MOS differential amplifier and the actual MOS differential amplifier. Then we will go to the large signal analysis as well as the small signal analysis of MOS differential amplifier. And in that large signal analysis, some mathematical derivation is there. Small signal analysis, circuit level derivation, we will do that. And the last topic is MOS differential amplifier with the various type of loads for improving the gain of the amplifier. Okay, so first we will start with a differential amplifier. So differential amplifier is nothing but an amplifier whose gain or whose output is the amplified version of difference between input signal. It have two inputs, V in 1 and V in 2. The output will be V in 1 minus V in 2. So differential amplifier amplify the difference between two inputs. So it use a concept called differential signaling. So due to this differential signaling itself, this amplifier has so many advantages. Differential amplifier have so many advantages, or its noise immunity is high, noise performance is high, performance is high, and it have large output swing, and due to the MOSFET implementation, large input impedance, and it can tolerate the power supply variation it can tolerate. So etc, so many advantages are there. I think all these you studied in analog integrated circuits or linear integrated circuits in fourth semester, no, in fifth semester. Okay, so first we will start with a basic differential amplifier. It will amplify difference between two input signal. That's why it is called a differential amplifier. The main advantages of the differential amplifier, we said it is noise performance is very high, or it will reject or any type of noise, coupling noise, or so environmental noise it can reject, or it can reject the power supply noise. I think we are familiar with the term power supply rejection ratio, and it can reject any other noise like coupling noise will be there, coupling noise, etc. It will reject, and it provide higher output swing, because most of the differential amplifier we are taking differential output or double-sided output we are taking. So due to that, the actual swing is 2 times the single stage output swing. Also due to the rejection of, here we are familiar with one more time, the average value of V1 and V2, it is called the common mode, or the DC level of the input, is also rejected in differential amplifier. So due to the rejection of common mode signal, it can give higher output swing and higher gain it can provide. We know op-amp, the actual ideal gain is infinity, and its performance is in linear region of amplifier, so more linear performance it will give. So the noise due to the higher order frequency terms are absent in differential amplifier. So these advantages are important. And actually these advantages, most of the advantages, noise rejection, etc., are come from the basic concept of differential signal. So here we are discussing difference between the single-ended signaling and differential signaling. Single-ended signaling, the signal is defined with respect to the ground. And in differential signaling, we are taking the signal with respect to, or the measurement is taken with respect to two terminals. Okay, and usually this one is the differential signaling is used in differential amplifier and op-amp. Differential amplifier and op-amp we are using differential signaling. This differential signaling will give high peak-to-peak signal or large swing in the output, large swing in output due to the rejection of common mode signal, and high immunity to the all type of noises like environmental noise or the coupling noise or due to the power supply rejection, etc. Because all the noise we are expecting, not practically, we are expecting that all the noise are affecting both the input terminal in a similar manner. So when we are taking difference between these two, that noise will cancel each other. Here, if we are assuming there will be a noise Vn here and one more noise Vn here, then the signal at the the measuring terminal is Vn1 plus V noise, and here it is Vn2 plus V noise. So when we take the difference of these two, the noise time will cancel. That noise is coming from any manner. It is from the thermal noise, or it's from the power supply noise, or it's from the coupling noise. Coupling noise means the coupling between two connecting wires. That will also introduce a parasitic capacitance or coupling effect. That also we can that effect also we can reduce using the concept of differential signaling. So here now we just discussed what are the advantages of differential amplifier. Actually, main advantages are come from the concept of differential signaling, the noise rejection, common mode signal rejection, and swing improvement. And next we will discuss with the differential amplifier or most differential amplifier. This is the simplest differential amplifier. Actually, this consists of two common source MOS amplifiers only. Here, this will be one of the common source amplifier 1, and this one will be common source amplifier 2. Now, this one will also act as a differential amplifier. If we consider the common source amplifier 1, the input is V in 1. The output will be, as per the if we are neglecting channel length modulation lambda equal to 0 and body effect gamma equal to 0, then the output we can write it as minus gm 1 into rd into V in 1, and here I am assuming both transistors having same transconductance. Then for V in 2, output V02 is minus gm rd into V in 2. Then this one will be V out 1. Okay, V out 1. Then the net output between these two nodes, actual output V0 is nothing but, if we give plus here and minus at the second amplifier, V out will be V out 1 minus V out 2, and the output is minus gm rd into V in 1 minus V in 2. Or this indicate that this simple circuit will act as a differential amplifier. For the implementation of differential amplifier, this one is enough. But this circuit have some drawbacks. Drawback means we are assuming that for any input V in 1 and V in 2, the output must be like this. And for any differential input of, if I give here it is 5 and 5.1, I am expecting, if this one is 10, I am expecting minus 10 into the difference 0.1, that is 1 volt. And for even if it is 6 and 6.1, I am expecting the same output. and input is 10 and 10.1, I am expecting the same output in general. So for if it is a differential amplifier, it need to give a differential output 1 volt, differential gain output, the output here it is 1 volt for any differential input of 0.1. But in this circuit, the main drawback of this circuit is that its drain current ID1 and ID2 is largely depend on the common mode signal. So due to that, there are some drawback. The output may be like this, but due to the large common mode signal, the output may be the clip off. Output may be clip off because if we are giving 10 volt VCC, due to this bias voltage, the reference will be, the DC reference will be 10 volt, or assume it is okay 10 volt, and we are expecting an output of, sorry, assume it is 9 volt and we are expecting an output of 2 volt. Okay, 2 volt like this. That means it will vary from -7 to 11. Then due to the 10 volt limitation of the VDD, the output look like this only. Okay, output look like this only. Some portion will clip off. If we vary the common mode signal in this differential amplifier, ID will vary, and that will vary the biasing of the transistor or the DC level of the output transistor, and which may create a clipping in some level. It may be in the positive level or maybe in the negative level. Okay, so to overcome that one, or keeping this biasing is a fixed level, or the keeping the ID value, drain current is constant, or drain DC level is constant irrespective of this common mode signaling level, we are modifying the circuit like this. Here we are using an extra connection ISS. ISS designed such that the value of ISS equal to ID1 plus ID2. Here it is ID1 and ID2. Under any this is an ideal current source, so the current through this this node always constant, it cannot vary, so always it will keep the current ID1 plus ID2 is limited to ISS. Okay, that's advantage. So using this we will discuss the actual differential amplifier. So any value of common mode signal, if the common mode signal is 5 volt, or it is 1 volt, or it is 10 volt, for any value of common mode signal, the current through both the transistor are fixed. If the common mode signal is any value, it will be both ID1 and ID2 are equal. If we assume M1 and M2 are identical, then for any common mode signal, CM indicating the common mode signal, ID1 equal to ID2, and which is ISS by 2. Okay, so that is the advantage of this circuit. If we give any common mode signal, the current through M1 and M2 are fixed, and its value is ID1 equal to ID2 equal to ISS by 2. So here we can write one more thing. If we consider these two signal are shorted, and we are giving some common mode signal VCM, what will be the output of this circuit, and or how it will be performed, we will analyze that. So if V in equal to V in 1 equal to V in 2, and which is equal to VCM, and we have ID1 equal to ID2, sorry, ID1 plus ID2 equal to endana, it is ISS. This condition is true under any input condition. Okay, and we know the basic drain current through the transistor id equal to 1 by 2 mu n coax w by l vgs minus vth the whole square under saturation. We are assuming all the transistors in saturation for the amplifier operation. So in this circuit both Vg1 equal to Vg2 shorted together as well as Vs1 equal to Vs2. Therefore, under short circuit or common mode condition, ID1 must be equal to ID2. By using these two equations, we can prove that ID1 equal to ID2, which is equal to ISS by 2. Then, what is the output voltage due to this common mode signaling? So if we measure the output voltage, assume these the Vx and Vy be the output voltages, so this one we can measure using KVL, KCL, Kirchhoff voltage law. VDD is the total voltage. VDD minus this IDRD, we will get V01, or the value of V01 equal to VDD minus ID1 RD, which is equal to VDD minus ISS by 2 RD, and V out 2 equal to VDD minus ID2 RD, also that also same as that of VDD minus ISS by 2 RD. And if we take the actual output V out, we will get V out 1 minus V out 2. Both are same, so the output voltage is 0. This will be true for any value of VCM. Okay, so this is the common mode operation of a ideal differential, most differential amplifier. In practical case, we need to consider difference between GM1 and GM2, RD1 and RD2, etc. Here we are assuming an ideal differential pair with both the transistor are identical, RD1 equal to RD2 equal to RD. Then what happened? Okay, I forgot one thing. We'll add one more slide. What happened to this one if we are giving and what happened if we give differential signaling? Okay, so differential signaling also we will check. If you are giving a differential signaling like input is given like here we are giving VD, or we are assuming this differential signaling is split into two equal parts. So the V in 1 we will assume it is VCM plus VD by 2, and V in 2 equal to V in 1, V in 2 equal to VCM minus VD by 2. Then let ID1 be the current or ID1 equal to ISS by 2, which is equal to ID2 be the current due to VCM, and delta ID1 be the current change due to VD by 2 in M1, and similarly delta ID2 in M2 due to it's minus delta I2 decreasing, it is due to our minus VD by 2. Using the concept of transconductance, we can write this delta ID1. So here the current is ID plus delta ID. This delta ID is due to the differential signal. Here it is ID minus ID1 plus ID2 plus delta ID2. Here it is instead of plus, here it is minus, because we are assuming a negative supply here, minus VD by 2 differential signaling. Here it is plus VD by 2 we are assuming. Okay, so the value of delta ID1 become GM into VD by 2, the small signal analysis of MOSFET in terms of transconductance. So delta ID2, we will get it is minus Gm into Vd by 2 because we are applying a negative voltage at the second input. Then we can write Vout1 equal to VDD minus ID1 plus delta ID1 into RD, or it's become VDD minus, we can write it is ISS by 2 into RD minus that value is GMVDS by 2 GMVD by 2 into RD. And similarly VO2 also we can write it is similar to this one, VDD minus ISS by 2 into RD. There it become plus GM into VD by 2 into RD, because here in plus delta I2 the value become minus GM VD by 2. I made a mistake here. Here also it is I2 plus delta ID2 by 2. ID2 plus delta ID2 by 2. This delta ID2 by 2, delta ID2 itself a negative value. Okay, so when we can find the value of actual output Vout, it is Vout 1 minus Vout 2. Then we can cancel two quantities here. This VDD will cancel and ISS quantities will cancel, and only these two will remain. So the result become minus GM into RD is taken outside. It become VD by 2 plus VD by 2, or it's become minus GM RD into VD. For the differential gain of this differential amplifier AD, we can write it as V out by V, which is equal to minus GM into RD. So this indicating a basic working of Morse differential pair. So just go through this one. First one is the common mode signal. We got output is 0. For differential mode signal, we got output is minus GM RD into VD, or the differential gain is minus GM RD and common mode gain is 0. So next we will go to an analysis of, actually first we will start with the qualitative analysis of differential amplifier for the differential input, and then we will go to qualitative analysis of differential pair towards the common mode input. Meaning is that qualitative analysis means how much input signal we can give to the circuit, or what is the range of input where the amplifier will operate satisfactorily. In the qualitative analysis of Morse differential pair for differential input, we need to find the value of V in minus V2, V in 1 minus V in 2, where this circuit will act as a differential amplifier. From the graph, we will get an idea that, so this will be the plot versus V01 minus V02 output, actual delta output versus delta input. So this is the actual output of V0 versus V in, differential in, VD in. So in that, only this region of operation, this transistor can act as a amplifier, because in this region of operation only output and input have a linear relation. Okay, linear relation. In these regions output are saturated, and there we can't use the MOSFET or Morse differential amplifier as an amplifier. Okay, so we need to define what is the region of operation. And similarly, in common mode signal VCM, we found that the common mode signal, earlier we discussed when the common mode signal is varying, in this amplifier circuit the output may clip off or something may happen, or the distortion will be there. But in the actual differential amplifier with the current source or current tail current source there, The common mode signal is independent. We said it is independent, but in practical amplifiers, this is not an ideal current source. This current source is created by a MOSFET, like a MOSFET biased as a current source. Then, so there will be practically there will be a limitation of VCM. So, what is the range of common mode signal that we can apply to a MOSFET? We will discuss. Just okay. First, we will go through a brief discussion. That's all. So first we need to analyze what is the working of this differential amplifier when V input minus V input 2 vary from minus infinity to plus infinity. So first we will check the output. Okay, first case, when V input 1 equal to V input 2, both the transistor are biased the same. Say for V out 1 equal to V out 2 and V0 is 0. V0 is measuring between these 2 points, plus minus, here it is the V0. Okay, so then what happened if when V in is increases, or V in 1 minus V in 2 increases, what happened here? The M1 will conduct more, and M2 conductivity decreases. So due to that the V0 1 or V out 1 decreases, and because when more current is gone, the voltage at this point decreases and V out increases because here the current is low. Our output we defined as output is VDD minus ID RD for each stage. V out I is AI. When V input increases, means ID1 increases, so output is decreases. So V out 1 decreases and V out 2 increases. V0 goes to a negative value. And again, if we increase V in 1 minus V in 2 to a large value, the conductivity of V1 increases very large, and the voltage base, the gate voltage of V into is low. The M2 become off. Okay, M2 become off. If M2 is off, if the voltage at this point become VDD. Okay, because if this is off means V out 2 is VDD minus I2 is 0, so it is VDD itself. And when M1 is fully saturated, okay, the V in 1 minus V in 2 is such a way that M1 is fully saturated and M2 is off. Then the V out 1 is VDD minus, it is ID1 become ISS because I2 is 0. So VDD minus ISS into RD, and the difference we will get, the output is minus ISS into RD. This one shown here, right? In this graph, the same is shown here. When V in 1 minus V in 2 increases, beyond some particular value, ID1 become on or ID2 become off, and entire current flow through the ID1. Okay, here entire current flow through the ID1. So there the voltage is VDD minus ISS into RD. Here it is VDD. So when we take the difference, it's become minus ISS into RD. In the reverse manner also we will get it is like when V in 1 minus V in 2 decreases or increase in the negative direction, M2 will conduct more, M1 will conduct low. So output increases in the positive direction and it is saturated after at some point. And this point is where these are the points or region where one MOS is off, one MOSFET is off, one MOS is off. So here we need to find where this MOSFET is switched off, or up to that differential signal only this device can handle. Okay, so it is an important analysis and we will do that also. uh, keep make a copy of this one. Here I think I need to delete all this. I need to find where at what value of V in 1 minus V in 2 one of the transistor become off. So for that we are using we are considering the point P. Point P is a reference point. With respect to P, we will write I think in text note I given is that with that we will consider what is the condition for switching off one of the transistor. So first we will write with respect to this one V in 1, here it is VGS1, here the voltage is VGS2. We know the value of VZ from the first transistor. Here we can write VZ is V in 1 minus VGS1, and also VZ from the second transistor like this one, V in 2 minus VGS2. And from these two equations we can relate V in 1 minus VGS1 is equal to V in 2 minus VGS2, and V in 1 minus V in 2 we can write it as VGS1 minus VGS2. So instead of finding what's the value of VGS V in 1 minus V in 2 to make one of the transistor off, we can find the value of VGS1 minus VGS2, which makes the one of the transistor is off. So how we will find the VGS1? Okay, so if the current through these transistors, we know this one is I1, ID1, this one is ID2, then we know ID1 is in saturation condition 1 by 2 mu n COX W by L into VGS minus VTH the whole square, or we can write VGS as root of 2ID, VGS1 is 2ID1 by mu n COX W by L plus VTH. Similarly, we can find the value of VGS2 also. VGS2 also root of 2ID2 by mu n COX W by L plus VTH. I am assuming both having same threshold value. So under the condition of one transistor off, if M2 off means ID2 equal to 0, the value of VGS2 is nothing but it is VTH, and the value of ID1 become ISS, because on off IL, if this one is off means entire current ISS will flow through ID1, and we'll get VGS1 equal to root of 2 ISS by mu n COX W by L plus VTH. Then the value of V in 1 minus V in 2 for switching off one of the transistor, which is equal to VGS1 minus VGS2, which is equal to nothing but root of 2 ISS by mu n COX W by L. Or in this graph, the switching region here both the case, the magnitude of these two value is nothing but root of 2 IDSS by ISS, sorry, ISS, mu n COX W by L will be there. So for the proper operation of differential amplifier, the differential input must less than this one. This is the cutoff voltage. Okay. Similarly, we need to evaluate what is the range of common mode signal that we can apply. So this will be the expression of common mode signal that we can apply to a differential amplifier. Why it is, we will discuss that. With that, we will wind up the first section. Okay, so here this is a practical differential amplifier. Here the current source is replaced with the MOSFET M3. Okay, and it is biased as a current source. So as per the derivation or derivation we will explain. As per the derivation, we will get the value of common mode signal. The common mode signal at this one must greater than VGS1 plus VG3 minus VT, and this value much less than the minimum of VDD or VDD minus IDSS by 2 RD plus VT. So this minimum you can neglect. Actually the value must be less than VDD minus ISS by 2 RD plus VT. So how this value? Okay. So for the basic idea, for the proper operation of sorry okay sir, for the operation of differential amplifier M1 and M2 must be in saturation. Okay, must be in saturation. For any MOSFET in saturation, we know VDS must greater than VGS minus VT. Here, for the both transistors, that if we consider one of the transistor, if we consider this as the transistor, the VDS value drain to source, or we can write it as VD minus VS greater than or equal to VG minus VS minus VT. So S was we can cancel each other, or VD must greater than or equal to VG minus VT, or the value of gate voltage must less than VD plus VT. Then only the transistor, this M1 and M2, is in our saturation mode. So this from this one we will derive this condition: V in common mode must less than VDD minus ISS by 2 RD. Because in common mode operation, in common mode operation, ID1 equal to ID2 equal to ISS. Therefore, the value of VD we can write it is VDD minus ISS by 2. Oh, sorry, here it is ISS by 2. Okay, both are equal. ID1 and ID2 are equal, and sum is ISS. ID by 2 into RD. Therefore, the value of VG, VG is nothing but the common mode signal VM must less than or equal to VDD minus ISS by 2 into RD plus VTH. Okay, and also one more thing is there. This value may sometimes it is greater than VDD. That's why we limited it to VDD. Okay. Anyway, this value will not go beyond VDD plus VTH. And next one, the second minimum condition we need to evaluate, VCM. This VCM for the proper operation of the okay, I think I need to take one more slide. So the second half, or if we consider the this region, for that we will consider the lower part. Okay, lower part of this one. So for the proper working of M1 or M1 in saturation, VGS must greater than VTH ആയിരിക്കണം. That's all. And that means the VG minus Vs greater than VTH, or the VG is greater than Vs plus VTH. So just here we need to define the value of Vs. What is Vs? The source of this one is here P, and this source is nothing but drain of M3. Okay, drain of M3. So here all we can use VGS1 S1, VG1 S1. The previous slide also please give that symbol. So if we consider this one, VG must greater than VS1 plus VTH. And what is VS? VS means this value. So for proper operation of M3, for M3 we know VDS is greater than VGS plus VTH, so that drain source voltage or the value of VD must greater than VG plus VTH. Oh, sorry, not plus, VGS minus VTH. Okay, VGS minus VTH. So VD3, VG3, here also will give 3. So we know the drain voltage, the VS1 equal to VD3 is greater than base voltage minus here the gate voltage of the M3 VB minus VTH. So therefore VG1, which is equal to VCM, is greater than or equal to the VS is VB minus VTH. Actually okay, VB minus VTH plus VGS1 itself they given. So there is a missing, sorry, Vin is greater than VGS3 minus VTH, this one itself, and VGS2. Oh, I think these derivations are not required. This much is not required. Sorry for that. So VCM is nothing but here plus minus VGS1, and here it is VCM must greater than or equal to this voltage must greater than or equal to VGS1 plus this voltage is required, and from this one we will get for the proper operation of M3 plus VP, or for here we can give equal to VCM is VGS1 plus VP. For proper operation of M3, the value of VP or the VD3 must greater than VGS3 minus VTH. So then only this one becomes saturation and it can act as a constant current source. So the value of VCM, this equality changes to greater than or equal to due to this sign in VP, VGS1 plus VGS3 minus VTH. The same thing we will get it as VCM must greater than or equal to VGS2 plus VGS3 minus VTH if we consider this path. Okay, that's why they given VGS1 or 2, 1 comma 2 plus this quantity. Okay, that's all. So next section we will analyze what is the working of differential amplifier. Okay, for large signal as well as small signal. I think large signal amplifier I just will go through that one and we will derive the small signal analysis. Okay. And one more thing we need to finally we need to discuss here is what is the output swing of differential amplifier. So the maximum output of differential amplifier is nothing but it is limited by VDD, and the minimum one is limited by V out minima is VCM common mode minus VTH, because the minimum output here must keep this transistor is in saturation, or the value of VDS must greater than VGS minus VTH. That's why if we give some common mode signal, the drain output VDS drain output V out minima is VGS minus VTH, or VCM common mode signal minus VTH will be there. So the common mode signal will limit the output swing of differential amplifier.